Hey, Eric.
Hi, am I the only one here?
Yeah, I'm admitting people in. So there's Kenny, you, and David. I think, and Leo, of course. So far, we have 5 people.
Then, oh, I think all of their videos off. Okay, now one of them is on.
Okay, all right, let's get started. Let me share my screen. Okay, so I think all of you were in the session last week, right? So you're all familiar with the method we talked about to share the mooncake, the stars and bars. Right, last time we discussed problem 1 and 2. Okay, so today we're going to go over 3 and 4. Who want to talk about number 3?
I'm probably not going to get this one right, but so can you put up the paint thingamajig?
Yeah,
Paint
hold on.
3D.
Is that Eric?
Yes, I'm Eric.
Yeah, so when I don't see your face when you are talking, so
oh, okay, here we
for
go.
anyone, yeah, please when you are talking, please announce your name so that I know who I'm talking about. Okay, so
Okay.
let's first go over number 3. So number 3 said Leo has to give at least 1 piece to each family member. So that's the same condition as problem number 2.
Yes.
And then it's asking what's the likelihood Leo gets more pieces than the number of pieces any other members get. Okay, so we have 5 people and Leo gets more than any of the other 4.
Okay, I'm gonna think this as I go through. So
okay,
yesterday we noted that there were 330 ways to distribute it out if everybody has to get one.
Okay, so can you briefly review how we got 330?
Okay. Okay, so you have 12.
Uh-huh.
And then everybody has to get at least 1.
Yep.
So that means you have to put 3 in between the spaces of the stones, 3 sticks in between the spaces. Because if you have one here and another, if you have one, so if
I put 3 sticks, that's to allocate among 4 people, right? But we have 5 people.
Oh yeah, 4 sticks.
Okay,
yeah,
4
I
sticks.
misspoke. Okay, so then you have to put them in between the spaces. Okay. So there's 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 spaces. So then we have to do 11 choose 4 to arrange the spaces.
Okay, so 11 choose 4. So we have 11 spaces and there were 4 sticks.
4 sticks.
So that will be 11 choose 4.
Yes, and that equals 11 times 10 times 9 times 8 over 4 times 3 times 2 times 1.
Okay.
Now you can cancel out the 4 and the 2 to cancel out the 8, cancel out the 9 with the 3, and you get 330 ways.
Very good. Okay, so this is from problem number 2, right? Number 2, there are 330 ways. If if Leo has to give at least 1 piece to each family member. Okay, now number 3. In what situation Leo gets more?
Okay. So since everybody has to get at least 1.
Mm-hmm.
I'm right about that.
Mm-hmm.
So that means that let's say that Leo gets the most possible.
Okay.
So Leo gets.
First situation, you're saying first situation is Leo gets most possible. How many?
He can only get 9 because no, he can only get 8 because everybody else has to get at least 1.
Okay, so basically Leo gets 8 and the other one gets 1, 1, 1, 1, right?
Yes, and then so there's only one way to do it that way.
Okay, so this is one way to do it.
And then now for the second case is that Leo gets second most as possible. He gets
that would be
7.
Okay.
And then so now one person has to get 2. There's 4 ways to so like let's say like you get 2 and everybody else gets 1.
Okay.
There's 4 ways to arrange the 2 within the 1s.
Okay.
So there's 4 ways.
Okay. 4 ways.
Now Leo has to get. Now Leo gets 6.
Okay.
That means that there are 6 left.
Okay.
So now we have to find out how to distribute this.
Okay.
So you can either do 3, 1, 1, 1. There's 4 ways to do that.
Okay.
Then you can do 2, 2, 1, 1. And I believe there are, let's see, 4 choose 2 ways to do that, which is 6.
Okay.
And I don't think you can do 3, 2, 1.
Okay.
And that's all. So 1, 4, 10.
Wait a second, Eric.
Yeah.
It says that Leo has to have more mooncakes. What's the probability that Leo has more mooncakes than any other person? So that means that wait a second, sorry.
So then now Leo has to get 5.
Okay.
So then 5. So now we have to try to arrange the 7. Nobody else. So then we can only do 4, 1, 1, 1. There's 4 ways to do that. We can do 3, 2, 1, 1. You have to now choose, so now that's 4 factorial over 2 ways to do that.
So that's 12.
Yes.
Okay.
And basically now you can also do 2, 3, and 1, 4. But that we already counted that, so there's only 16 ways.
Hold on. 3, 2, 1, 1, and then what? That's it, right?
Oh yeah, 2, 2, 2, 2, 1. There's also 2, 2, 2, 1.
2, 2, 1. So how many?
Oh, I thought that was it. I think that's what I got wrong. Okay, so now
okay.
there's only 4 ways to do it that way.
Okay.
And then I think that's it. Those are the partitions of 7.
Okay. So how many in total?
20.
20. Okay.
Now if you have 4, if Leo has 4 mooncakes, then there's 8 left. But nobody can get 4 because Leo has to have the most.
Okay.
So we can do 3, 2. We can do 3, 2, 2, 1. There's 12 ways to do it that way. Okay, so then we have to find the ways to do 5 without.
That's it. And 3, 2, 2, 1. Any other way to allocate 8 to the remaining 4 people?
What?
2, 2, 2.
2, 3, 2. We already have that.
2, 2, 2, 2, 2.
Oh yeah, 2, 2, 2, 2. I forgot that too.
Okay. Any other ways to allocate it?
4, 1, 2, 1. Or 4, 2, 1, 1.
No, you can't
Leo,
do that because Leo has to have the most. Because
Leo
if
has
Leo
more
doesn't
than
have
the
the
other.
most, then he will not be the king.
Okay. Well, this is different. So when Leo, if I say Leo has the most, then the other ones may get 4 because if they are both 4, Leo still has the most. I said Leo has more than any other member, so that means the other member cannot get to more than 3, right?
Right.
So any other ways?
I don't think so.
Give it another thought.
Can there be 3, 1, 3, 1?
3, 3, 1, 1. Right?
Oh yeah. Whoops, forgot that one too.
So how many?
That's
6.
Yep. I think that's it. And then what? So this is
then you have to add them up.
19.
Add
So
all of
why
them
not?
up.
why didn't you try Leo? Leo gets 3.
Because then it would be too much. It would be an overflow. Everybody
Right,
would
so-
either have more, or one person would have high with Leo or have more. Because
Yeah,
if you
so-
have 2, 2, 2, 2, that's 1 less than 9. Somebody's gonna
Okay.
have to have 3.
Okay, so there's no way we can have this one work. Okay.
Mhm.
So how many in total?
There are 1 plus 4 plus 10 is 15. 15
Okay.
plus 20 is 35. 35 plus 19. No, or I could just do it the easy way. 20 plus 20 plus 20 plus 10 plus 4.
You're almost done with the calculation and then you redo it, but that's fine. So your group 1 and 19, that's 20. So in total, that's what? 54,
20
right?
plus, yeah, 54. So now that's
So-
54, but there were originally 330 ways to allocate it.
Okay.
So now 54 over 330. Oh no, I have to calculate.
Come on, you don't need a calculator for this. What do
I
you-
know I don't. So that's
that?
also 27. That's also 27. No, not 27. Okay, that's also 18 over 110 because you cancel out a 3 from both sides. No, 18.
165.
No, it's 18. Yeah. So that's also 9 over 55.
Okay, so the probability is 9 over 55, right?
Yeah, I think so.
Okay.
I think.
I think of an easier way to do this.
Eric's. Yeah, and that's what I'm about to say. So I think I like Eric's way of counting this, but I think there is an easier way. So at least one easier way. So David, go ahead.
So basically, I divided this up in cases. 8, 7, 6, 5 are all
Okay.
fine, but then like I just devised this case. So basically,
What do you
Leo
mean
is
by
1.
765? You elaborate it.
Well, I mean, case 1 is that Leo gets 8. Case 2 is Leo gets 7.
So you
Case
divide
three.
it based on how many Leo gets, right? So 8, 7, 6, 5, 4.
Well, I mean, I have a new way right now, but
Okay. You have a
So-
new way, all right?
so basically, Leo is one of the 5 people. So with like there are cases in which he gets the same. So like, we have to minus that. So the original one would be 1/5, which is
Go ahead.
the original probability would be 1/5 or 11/55. Oh, 11 over 55, not 9 over 55.
What
So
do you
that
mean
would be
by 1/5?
because like everybody has the same portion. So like
Okay. So
if
you're
you
saying
don't count
everyone
the repeats.
can be high, may get more than the others. So there are 5 people. So you said the original probably is 1/5, but it's not exactly right because they may get the same. They may.
Yeah, so like that would be 66.
What do you mean 66?
66 ways out of 330.
Okay.
And then you start to a minus. So let's just say that Leo gets 4 cookies.
Leo gets 4. Okay.
Originally you could have gotten x plus y plus z equals 3. X plus y plus z equals 4. Well, I mean, no. So x plus y plus z plus w equals 8.
Okay. So basically, the other 4 people, x plus y plus z plus w equals 8, right? So these are the other 4 people. How many they are getting, right?
Yeah, and then w equals 8 minus x plus y plus z.
Okay.
And that is basically an x plus y plus z can equal 3 all the way to 7.
3 all the way to 7. Okay.
But we omitted 3 and 4 in Eric's case because they do not work. But we're gonna omit it right here. So
5,
3 and 4,
7.
3 and 4, 3 has 1 solution and 4 has 3 solutions.
Okay, 3 has one, originally had one solution, 4 has 3 solutions.
So 54 is 11 away from 66. So we want to eliminate 11. And
No, hold on.
12,
you don't know 54
12.
yet.
Oh.
You started from 66. You don't know 54. Okay, that's the answer. All right.
And then we have to see Leo gets 3, 2, and 1.
Okay, so Leo gets 3.
X plus Y plus Z plus W was 9.
Okay. Keep going.
So W equals 8 minus X plus Y plus Z.
8, 9, right?
9. I mean 9, yeah.
Okay.
Yeah, I don't think I'm on the right track here.
All right. I understand you're trying
It's
to
kinda
minus
confusing.
something, but actually, in your situation, okay, in your example, I don't even know if this is part of it. I mean, Leo, because the other ones won't get 3 to beat beat uh, to beat the other the other family members. So I'm not sure if this will work.
Well, I mean, 9 or above is impossible because one of them will get 0. That does not follow the case. So that's why I did 3 and minus. 3 and below.
3 and below, but I'm not sure how you complete it. You think this will work? If you think this
I mean,
will
I didn't
work,
really complete it. I thought it would complete. I thought it would work, but it didn't.
okay, you can keep thinking, right? So if you figure out, send me an email, okay? All right.
Okay.
Any other solutions? There must be an easier way than Eric's. Okay, go ahead, Leo. Make sure you get most, all right?
Okay.
Okay.
So in here, you first just start with there are a total of 330 ways.
Okay, so 330 ways.
So first allocate the 5 pieces that each person must get.
First, allocate 5 pieces. So let's say we have person A, B, C, D, E. So you gave each one of them 1, okay?
Okay, so now just ignore them because you know they're there.
Okay,
So
you know they're there.
So now you have 7 pieces left.
7 pieces left.
So you know that Leo will get the most.
Uh-huh.
So 7 divided by 5 is a little bit more than 1.
Okay.
Oh yeah, 1.4. So then you know that Leo can't get 1.
Right, so Leo cannot get 1. If Leo get 1, okay, the other ones have to get zeros. Right, so that's not 7.
So Leo has to get greater than 1.4.
Leo has to get more than the mean, 1.4, okay?
So he has to get at least 2.
Leo will have to get, so these ones won't work. So Leo will have to get at least 2, okay?
So then there would be 5 left.
Okay.
And there is a possibility because now someone can get 0.
Okay.
So now wait. Yeah. So now if someone can get 0, there's a possibility where for example, like there will be 5 left. If it's like 5000.
5000.
Yeah. So then it wouldn't follow the rules.
Okay, so 5 is more than 2. This won't work.
So in here you just count how many different ways.
Okay, you can count. Okay, so this won't count.
So you have 4 people into 5.
Okay.
So wait, actually it won't work.
Okay, so why it won't work?
Because no matter what, someone will at least get 2.
All right, because you have 5 pieces and you have 4 people sharing these 5, so someone will get 2.
Yeah.
All right, so this won't work.
So if it's 3.
Oh, this won't work. If it's 3, okay.
Then no matter what, it will work.
No matter what, it will work.
Actually, no.
Okay. So if 3, you have how many left?
Yeah, 4 left.
Okay. 4 left.
So, and here you count them.
Okay. Count.
So it's 4 into 4. So one possibility is 1, 1, 1, 1.
Okay.
Another is wait, and there's one way to do it.
Okay. So this is one way.
What? Yeah, and then you have 2, 1, 2, 1, 1, 0.
Okay.
And there is there is 12, and then you have 2, 2, 0, 0, and there are 6 ways.
Okay.
And then no more left.
Okay.
So in here there are 19.
Okay.
So for 4 and above, it will always work.
Okay. What do you mean by always work? So when Leo has 4, what do you mean by always work?
Like everyone will always get less than Leo.
Yep, because if Leo gets 4, the other 4 people has how many?
The other 4 people have up to 3.
Up to 3. So no matter, even if you gave all 3 to one person, that's still less than Leo's, right? So then what?
So then you can first give out the 4.
Okay, yeah, I gave out the 4.
So now you basically have 3 left.
3 left.
And you allocate them into 5 people.
How many people?
5.
Oh, 5. Oh, okay. So you gave 4 to Leo first, okay? And then you gave the remaining 3 to these A, B, C, D, E to 5 people, okay?
So it's basically out of 7 objects, choose 4 to be bars.
All right. So there are 4 bars you need to put, and there are 3 mooncakes, right? So this is 7 choose 3 or 7 choose 4.
Yeah.
Okay.
7 choose 3 is easier. So that's 7 times 6 times 5 over 3 times 2 times 1, which is 35.
Okay.
So you add 35 and 19, get 54. So it's 54.
All right, you're getting 54 over 330. Blah, blah, blah. Okay. So see, the shortcut is this. Once you figure out 3, okay. So Leo gets 3. This is complicated because you have 4 left, and you want to make sure the other ones don't get more than Leo, right? So after that, then when Leo gets 4 or 5 or 6 or 7, these all can be lumped into one case. 4, 5, 6, 7. So that's equivalent to this, right? 7, 8, 7, 6, 5, right? All right. So basically, at this point, you first gave Leo 4, and then you have 3 mooncakes left, and then you are allocating the remaining 3 to these 5 people. So any one of them may get 0. So you got 35. Okay, very good. All right. Any other questions about this problem?
I'm actually kind of confused on the last one. So you said 1 and 2 doesn't work, 3 works, and 4, 5, 6, 7 can be in one case.
Okay. Yeah. So after you figure out the 3, let's say you first gave each one of them 1, right? And then you have 7 left, and these 7, if you gave Leo 3, then the case is a little complicated. You have to discuss them, do this case work one by one. Okay. After that, if Leo gets 4 or more, okay, if Leo gets 4 or more, we're trying to figure out how many ways can Leo get 4 or more. Okay. So how to do that? Because we want to make sure Leo gets 4 or more. So we gave Leo 4 first. Okay. After we gave him 4, we have 3 mooncakes left. And these 3 mooncakes can be allocated to any of the 5 people, right? So let's say if we gave 1 to Leo and 2 to someone else, that means Leo in total gets 5, and the other ones get other. I mean, of course, you'll be adding the first one as well. Which for now we ignore them, right? So it's in total, we're allocating 7 to these 5 people. This problem is equivalent to allocating 7 mooncakes to 5 people, with Leo getting 4 or more. Okay, how many ways we can allocate 7 mooncakes to 5 people, with Leo getting 4 or more, right? So basically we gave 4 to Leo first, and then gave the 3 remaining ones to all 5 of them, right? And then that's what we are trying to figure out. We have 3 mooncakes and 5 people, so we have 4 bars, and then how to allocate these, how to shuffle them, right? Clear?
Well, I mean, for case number 6, aren't you allocating 1 to 5 people? So should it be like 4 bars and 1?
We were not discussing this separately. Okay, so if you want to do, let's say if you gave Leo 6, that's equivalent to give Leo 4 first, and then among the remaining 3, you gave 2 of them to Leo, and then 1 of them to some other people, right? So these 4, we are lumping them together. These 4 cases, we are not separating them, right? So if you look at Eric's solution, so Eric's solution is separating these ones, count them one by one, okay? And Leo's solution says, since we have 7 left, and Leo will get at least 4. So we just gave 4 to Leo first. This is similar to the first step we did. Since everyone will be getting at least 1, so we just gave 1 to each person first, and then we allocate the remaining ones. Got it?
Oh, yeah, I got it.
Okay. So let's look at the last one. The problems are getting trickier and trickier, right? So the last one said Leo has to give at least 1 piece to each family member. So this is the same as the condition in problem 2 and 3. Okay. And there's another condition. The other condition is Leo has to give more pieces to the parents, okay, to each parent than any kid. So there were 5 people, 2 of them are parent, okay, 2 of them are parents. So let's see, number 4, okay. So there were 5 people, A, B, C, D, E. Okay, let's say A and B, they are parents. They need to get more pieces. Each one of them need to get more pieces than any of the kids, because parent eats more. Okay, so how many ways can we do this? Anyone want to try this?
Kyle?
Okay, go ahead, Kyle.
So first, you can first give out 1 mooncake to each person.
All right, satisfy the first condition. We're giving 1 to each of them. Okay, then what?
So then you will have 7 mooncakes distributed to 5 people.
All right, 7 mooncakes left to 5 people.
So you can draw first like a little chart for the first case.
Okay.
In this case, the parents get all the mooncakes and the kids don't. Well,
Ooh, wow. Okay, so the parents get all. Okay, the parents will be getting 7. All right, and the kids get 0. All right. Okay.
Okay, so then there's well, first for the zeros there will be 1 probability, which is all zeros, and then for the 7 you can have 1 and 6, 2 and 5, 3 and 4. So that's 2 and 5, 3 and 4, and then that's 3 probabilities, and then you can multiply by 2 because you can switch them around.
All right. Okay.
So there's 6 probabilities.
6. Okay.
And then the second one, for the kids get 1, and then the parents get 6.
All right, kids get 1 and parent gets 6.
So for the parents, there would be 2 and 4, 3 and 3, and 4 and 2.
Okay. So why don't you do 1 and 5?
Because then one parent will have equal amounts to a kid.
All right, because you're allocating 1 mooncake to 3 kids, and one of the kids must be getting this 1. So in order for parents to get more than the kids, then the parents will have at least 2, right? So there are 3 possibilities.
So it's 3 times 3 because there are 3 possibilities.
3 first, and then depending on which this mooncake is being allocated to, let's say this mooncake may be given to Leo, maybe given to Angela, maybe given to Ela. So each one of them may get this mooncake. So that's 3 times 3. So that's 9, right?
And then if the parents get 5 and the kids get 2.
5 and 2, okay.
So first, if you say that 2 of them get 1, there's 2 cases. So it's
1, 0.
That would be 3 times, and then on the other side there would
This is 3 ways: 1, 0, 1, and 0, 1, 1. So this is 3 ways.
And then on the other side there would be 2 and 3, 3 and 2. So that would be 2 times 6.
Oh, 2, 3, and 3 and 2. Okay. So this is 2 cases. So this is 2 times 6, 2 times 3. That's 6.
And then if, well, you can't do it if it isn't possible if one kid gets 2 mooncakes, because then.
So if one kid gets 2, what happened?
Then the parents, one parent must have the same amount of mooncakes with one child.
All right. So if one of the kids get 2, parents have to get at least 3. But we only have 5 mooncakes, so there's not enough for me and my wife, right? So this won't work. Okay.
And then that's pretty much it.
There's one more.
I think there's one more where there's 4 and 1, 1, 1.
Okay, 4 and
3, 3, 1, 1, 1.
4 and 3. So that will be what?
2, 2, 1, 1.
2, 2, 1, 1, 1. There's one more case, right?
Yeah, and that's it.
Any other case we can think of?
No more.
So how many possibilities in total here? 6,
22.
9, 6, 1, right? 6 plus 9 plus 6 plus 1 is 22, right? Got it?
I have another solution.
Any other?
I have a Danish solution.
Okay. Yeah, David first.
So basically, what I did was I said parents sum can be 6, 7, 8, or 9.
Okay, so you do parent and kids. Parent sum can be 6, 7, 8, 9.
And kids sum can be 6, 5, 4, and 3.
Kid sum can be 6, 5, 4, 3. Okay.
Okay, before I start doing this, I'm gonna prove that when parents sum is 5 and kids sum is 7, it doesn't work. So
Okay,
when
let's talk about the 5 and 7.
When parents sum is 5, it could be 1, 4, 4, 1, 2, 3, and 3, 2.
Okay. 1, 4, 4, 1, 2, 3, 3, 2. Okay.
And so the kid sum can be, I'm pretty sure. I mean, the kid sum, there's like a lot. So.
Well, the kid sum is 7. It's not a lot. So there's only one number, 7.
15 cases. So that will be 1, 1, 1, 1, 5, 5, 1, 1, 1, 5, 1.
I think you're trying to enumerate all of these, right? Is there an easier way to prove this?
Yeah, we can omit all the 1s. With there are 3 cases. We can also omit all the 2s, and there's 2, 5.
Yeah, that's still
2,
counting
4.
this, case by case. I need an easier way to do this.
Doctor,
to prove this.
Me?
Okay, go ahead, Leo.
So for kids, at least one must get a 3.
Okay, why at least one kid gets 3?
Well, it is true that at least one must get 2, since 7 divided by 2 is like
7
7 divided by 3 is like 2 point something.
Okay, so the mean is 2 point something. So what?
But someone can't get a decimal, so someone must actually get at least 3.
So at least one kid gets at least 3. Okay. Then what?
But if the parents got 4 and 4, then it would already be too big.
All right. If there is a kid getting 3, that means the parent will have to get at least 4. 4 plus 4 is 8, which is bigger than 5. Right? Good. Okay.
So, like,
so we prove that. Keep going, David. Huh?
The kid with the largest number is 3. So like if you increase that, it will decrease all the other numbers, and so that will like be underneath the number parents get. Well,
Yeah.
for
So we have
6,
proved it. Okay.
for 6 and 6, we don't need to see if 1 5 works or 2 6 works, because kids are going to have, I mean, this mean is 2, so they must have 2 2 2, including 2s and
Okay.
including 1s, obviously.
Okay.
And so we only need to see 3 and 3. 3
Okay.
3. In 3 3, there's only one case, which is just 2 2 2.
Okay.
Because all the other cases, they have 2 or above.
Okay.
And then 7 and 5 are, we don't need to talk about 1 6 or 2 5 because of the same reason. And 3 4 and 4 3 are, we have 2 2 1, 2 1 2, and 1 2 2 that follows the same rules. So we have 6.
Yeah, so I think you are getting this pretty much similar to what who talked about this before? Kyle. I think this is pretty much similar to Kyle's solution then, right? If you are basically counting from bottom up, right? And Kyle counted from up down, top down, right? Any other thoughts?
Is there an easier way?
Okay, Leo.
So in here, the only way that one parent can get 1 would be if there's 1 6.
From which one?
Well, first give out the 5.
Okay, so let's say A, B, C, D, E, and first give out 5.
Now there's 7 left.
There's 7 left.
So the only case where a parent could get a 1 would be 1 6 and flipped around 1 6 and 6 1.
1 6 and 6 1. Okay.
And those are just 2 cases.
Mm-hmm.
And then you have
So that will be 1 6 6 1 0 0 0, right?
Yeah.
Okay.
And then you have 1 1.
What 1 1?
You can have the adults. But actually, then you can have the adults having 2 and 2.
2 and 2.
Yeah.
Okay.
Which will there's only one way, which is 1 1 1.
Okay.
So far you have 3 ways. And then you have 2 3 and 3 2.
2 3 3 2.
Yeah. So in these cases, there are 2 left. So then the only possible ones are like 1 1 zeros. There are 3 ways to do that.
What's the difference between this method and Kyle's?
No. I'm first doing the ones where you can't just like subtract.
Oh, okay.
Parents.
So you are doing a corner case first, right? Okay.
And then and then you must have 2 4 and 4 2.
Okay.
So in this case you have. In this case, there is 1 left. So with 1 left, there are 3 cases.
Okay.
And then for the last case, there is 5 2 and 2 5. Or there's only 1 way.
So this is 0 0 0, right?
Yeah.
Okay. So you're giving out one parent getting 1, one parent getting 2, and one parent getting 2, right? I mean, at least one parent get 2, okay?
And if both parents get at least 3,
Okay. If both get 3 or more, okay, then what happened?
then no matter what, the parents get more than the children.
Yeah.
So
Then parent more than the kid, okay?
so first give out the 6 and you have 1 left.
So you're giving them each one of them 3 first, and then you have 1 mooncake left to allocate to these 5 people.
Yeah.
Okay.
So it's 1 choose 5.
Okay. So that's 5 ways.
I mean, it's 6 choose 5. Wait,
You're giving 1 to 5 people.
yeah. Oh yeah. It's,
Why is 6?
yeah, it's 5 ways.
Okay.
So it's 5 plus the previous 5 plus 2 plus 6 plus 6 plus 2 plus 1 plus 2.
Okay.
So then that's 3, 9,
9, 3, 9, 15,
17.
17, 22.
Yeah.
Okay, good. So basically, you're discussing. You're trying to make it back to the case that we know at least someone getting so many, and then we allocate at least first, and then look at the remaining ones, right?
I think it wasn't that worth it because then
Yeah, this is okay. I think this is for me. I would
Dr.
probably
Hong.
prefer Kyle's way because it's more organized, and your way is organized too. We just have to be careful about these. One parent's getting 2 Ks. So if we have at least a parent get 2, make sure we don't miscount these ones, and the remaining part is easier, right?
Dr. Hong. So
Yes.
the last case was kind of confusing. Can you explain that again?
All right. So this is the same as the one before. So basically, Leo have decided, have allocated. Let's say the first case is if one parent is getting 1, if at least one parent get 1, okay, that means the kid will be getting no more than 0, right? So these cases are done. And then Leo was looking at if at least one parent get 2. Oh, this pen is not. Hold on. Let's see if Leo look at least one parent get 2. And then there are 1, 2, 3, 4 big chunks. So if at least one parent get 2, that means the kid will be getting no more than 1, right? Right?
Yes.
And then if at least, so after 2, if both parents, at least one parent get 2, if nobody get none of the parent get 1 or 2, that means they're getting 3 or more, right? If both parents get 3 or more, then it's guaranteed, no matter how you allocated the mooncakes, because the kid will be just get, there's only 1, no more than 1 left. So the kid will be having fewer mooncakes than parents, right? So that becomes, you allocate at least first. You allocate, since at least, each parent gets 3. So we gave them 3 first, and then there's only 1 mooncake left. Got it?
So like 3, 4, 4, 3.
Yeah, he actually didn't really care whether it's 3, 4, 4, 3 or whatsoever, because we have 7 left. Okay, we have 7 mooncakes, and we were giving at least first. We're giving at least 1 to. I mean, we're giving 3 to each parent. Okay, and then there is only 1 mooncake left. Give that 1 remaining mooncake to either the parents or the kids. That means the parent may, if you give that 1 to 1 parent, that means that parent will be getting 4 in total. Right? This is the idea of allocating at least. Look at this. The first step, we know if everyone get at least 1, we'll just give them 1. Give them each one of them 1, and then we play with the remaining ones. And then the last case is if we know, okay, each parent will be getting 3 or more. We just give them 3, each one of them 3 first, and then let's see how it goes. Right? Got it?
Yeah, kind of.
I'll give you guys a practice, okay? Prepare your pencil and paper. Oh, my Apple Pen is not working. I think it's probably battery off. So you listen to me carefully, okay? Back to this, the problem. So we said all the first 4 was based on me taking out 3 mooncakes. Okay, now let me take out 4 mooncakes. Okay, I take out 4 mooncakes, and I'm cutting each one of them to 4 equal pieces. Okay, 4 mooncakes. Each mooncake get 4 pieces. Okay, now I want Leo to allocate them. Okay, I want Leo to allocate them. I want to give at least 2 to each children. Okay, 2 to each child. Okay, 2 to each child. Each child will get at least 2. All right. And each parent will get at least 3. Oh, okay. How many different ways to allocate this? Each child will get at least 2. Each parent will get at least 3. How many different ways to allocate these mooncakes?
Yeah.
What's that?
Sunday.
Shh. Again, each parent will get at least 3. Each child will get at least 2.
Wait a second. How many people are there and how many mooncakes, just to make sure?
4 mooncakes. Each mooncake is cut into 4 pieces. Okay, and there are 5 people in my family. And each parent will get at least 2. There are 2 parents, 3 kids.
Well, I thought you said each parent will get at least.
At least 3. Each parent will get at least 3, and each kid will get at least 2.
Kyle, also I have to go now, actually.
Okay, that's fine. Let me see. Let me tell you if you got correct. Okay.
Okay.
Well, your answer is the same as Leo's first answer. I don't think it's correct. That's fine. You can keep thinking. Maybe I was wrong. I might use paper to do it again. But you can go. All right. You can watch the recording later. All right.
Did Leo say it's 70?
Yeah. Did you all get 70? Maybe I was wrong.
No, I didn't get 70. I'm not finished.
Oh, okay. How do you know Leo got 70 then?
I heard he's saying it.
Oh, okay. Okay, keep trying. Okay, guys, keep trying.
Can the parent be more than the kid, or is
I
there
didn't
really?
say the parent have to be more than the kid. I said
Oh, it has to
each
be
parent
at
will get
least. Okay.
I said each parent will get at least 3, and each kid will get at least 2. Oh, actually, it is 70. Yeah.
Yay.
Yeah, you're right. Okay, I was wrong. Okay. All right, is Kyle gone yet? I will tell him got it right. Yeah, Kyle's gone. So anyway, Leo, talk about how you got 70.
So you first start with the 16 mooncakes.
Oh, hold on. Why is this pen is not working?
You can use your finger.
Can I use my finger? How do you use finger? Does it take my finger?
What? It used to take your finger.
I mean, there's a settings thing that allows you to like once you pair your iPad with your Apple Pencil, like you can't draw.
Okay, now I can use my
Oh,
finger.
yeah.
All right. So okay, Leo, go ahead.
So you start with your 16 mooncakes.
16 mooncakes. Okay.
So you first give 6 to your children and 6 to your adults.
So I'll give 3 because I said at least 3 for each adult, and at least 2 to each child, right?
So that's a total of 12.
So these are 12 is gone. Okay.
So it's 16 minus 12 is 4.
16 minus 12 is 4. There are 4 left.
So it's really the equivalent of splitting 4 on 5 people.
All right. So how do I move up there? How do I
I
move?
think you need to use 2 fingers.
Oh, 2 finger. Oh, okay. That's smart. Yeah. Okay. Leo is smarter than me. All right. So now you have 4 mooncake left, right? And then you're giving these 4 to the 5 people, right? 1, 2, 3, 4, 5 people. You're giving 4 mooncake to 5 people. Okay.
So it's, can you draw the like 4 circles?
4 circles. 4 circles.
Yeah.
Okay. 1,
Well,
2,
any
3,
picture is fine.
4. Okay.
So it's basically add 4 bars.
Adding 4 bars because you're giving 4, allocating among 5 people, so you need 4 bars. Okay.
So it's 4 plus 4 is 8. So it's 8 choose 4 to be bars or 4.
So you have 4 mooncakes and 1, 2, 3, 4 bars. You need to shuffle them, right? So this is 8 choose 4. How many different ways to choose them? 8 choose 4.
That's 70.
Is,
well, 8 times 7 times 6.
Yeah, 70. Okay. Got it? So remember when you have at least, right? So basically, if it's at least, we just gave the, at least however many, gave that many to the people, and then allocate the remaining ones. Okay. Got it? Right? Any questions? If no questions, I will see you. Well, I think the next week is high schools. I will send out I will need to make the problems and then send it out and then decide when we're going to meet. Okay. So, oh, actually, no, next week we're not meeting. Next week I'll be very busy. So, and the week after, yeah, we'll meet the week after for those people who are trying to do the AMC 8. I'll be answering questions for AMC 8. So
Well,
I guess I'll see some of you in 2 weeks. Okay. Bye, guys.
Wait, so is it just a Q&A session?
Huh?
Is it just a Q&A session or is there like problems to do?
it will be before the session. I will be sending out a survey and see which problems you guys want me to talk about, and then I will discuss the problems according to the survey results. Let's say in the recent 6 years, if you pick problem, I don't know, maybe 2014 problem number 25. That's one of the problems.
Oh,
And
so it's
maybe
just like going
2018.
over the old AMC
Yes, I
problems?
will be going over some of the old AMC8 problems
Okay.
in the recent 6 years. All right.
And wait, for this problem, it says 8 choose 4. So the reason you got 8 is because like you're adding 4 more positions, 4 more bars.
Yeah.
To the end.
Yeah. It will be 4 mooncakes and 4 bars.
Okay, thanks. Bye.
Okay. Bye, guys. Oh, bye. All right. Bye.